Hey everybody, happy Mother's Day for all the moms out there. I'm just gonna chat today a little bit about limiting reactants. So this is picks up right from last week's lessons here. So let's first talk a little bit about what a limiting reactant is, and then we'll get into the actual problems themselves. So limiting reactants are the first reactant in a chemical reaction to be used up in that chemical reaction. When they are completely used up, if there's no more of that particular reactant, then you can't make any more product. And so the reason they call them limiting reactants is because they limit the amount of product that can actually be produced. So they limit the product that can be produced. Um, some reactants will not run out and they will be left over in a chemical reaction. Those particular reactants we call excess reactants. So for example, when I start this lesson in class, I always start talking about food and making food. So I'm going to do the exact same thing here. Let's pretend that I wanted to make a sandwich. So when I make a sandwich, I have a piece of bread. So this is bread. And when you make a sandwich, of course, you need two pieces of bread. And on that piece of bread, I add a slice of cheese and I add a slice of meat. And that produces one sandwich. Maybe we'll draw it out for those people who are visual learners here. There's my sandwich. And we got some stuff in the middle there. So you can see that when I talk about food, it's very easy to see that this is very much like a chemical reaction. We have our reactants here. We have some bread, we have some cheese, we have some meat, and I can produce a sandwich. Very much like we have reactants here and products over here. But oftentimes I find myself opening up the fridge and I don't always find everything in nice whole numbers. So let's chat a little bit about this. Let's say I had uh, um, 15 pieces of bread. Let's say I had 15 pieces of cheese, slices of cheese. And let's say I had 5 slices of meat. And I ask you now, well, how many sandwiches could I make given this amount of reactants? So I have 15 pieces of bread, I have 15 slices of cheese, and I have 15 pardon me, 5 slices of meat. And the answer, of course, is I can make 5 sandwiches. And the pen is not cooperating today. I don't know why. I'm not sure why that pen is not cooperating. Let's try the other one here. I have 5 sandwiches that I can produce. And of course, the question is, well, how did I figure out that I could produce 5? Well, as long as I have 2 slices of bread, 1 slice of cheese, and 1 piece of meat, I can produce 1 sandwich. So one of these three, either slices of meat, slices of cheese, or pieces of bread, is going to run out. So when I look at these, I look at what the maximum number of sandwiches I can produce with that number of that particular component is. So if I look at pieces of bread here, I can produce 7 sandwiches with this number of pieces of bread. Of course, if I produce 7 whole sandwiches, I'd still have 1 piece of bread left over. If I had this one and 15 pieces of cheese, and I look at that, I can produce 15 sandwiches with that because each sandwich only requires 1 piece of cheese. But when I look at pieces or slices of meat, I can only produce 5 slices of meat. So you'll notice that the slices of meat produce the lowest number of sandwiches, Once I run out of a reactant, I can't make any more product. In this case, our product is sandwiches. So that is the general idea of limiting reactants. They limit the reaction to how much product they can actually produce. As a result of this, we also get these two other reactants here that qualify as excess reactants. So once I determine the number of slices of meat that I have here that can produce the bread, I can actually determine how much of the other reactants, my bread and my cheese, I will have left over. So if I can produce 5 sandwiches total, it means that I'll only have 10 of the pieces of cheese left, and it means that I will only have 5 slices of bread left, even though it says here 7. I'll only be able to produce 5 because, or I'll only have 5 left over because, of course, each sandwich takes 2 pieces of bread. So that's the general idea of what a limiting and excess reactants are, and this example here is what I usually use in class. Students are able to pick this up pretty easily because it's a real life easy example with quantities that are easy to deal with in your head. Of course, in chemistry, quantities aren't easy to deal with in our head. We end up having, of course, to look at quantities using the mole, and so we're going to take that into account here. So let's go on to our first problem here. So it says here, what is the greatest amount in grams of magnesium oxide that can be created from a reaction between 7.8 moles of magnesium and 4.7 moles of oxygen gas? And then of course it says how much of the excess reagent is left over in moles. So I'm looking for grams of my product here, and I'm looking for how much excess reagent is left over. This is a stoichiometry problem. I cannot do stoichiometry problems unless I have a balanced chemical equation. So let's go ahead and write out the balanced chemical equation. I've got some oxygen gas, and it's going to react with some solid magnesium, and it's going to produce some solid magnesium oxide. And you guys have done this reaction in class. You've taken a strip of magnesium and burned it, very bright light, and of course you end up in a situation where you produce some magnesium oxide, which is almost like, it looks like soot. Before we even start this, we have to make sure that our equation is balanced. And so in order to balance my equation, I need to place a 2 coefficient in front of the magnesium oxide and a 2 in front of the magnesium here. Now, as I mentioned in the previous video in the stoichiometry problems, I always like to write down information about my reactants or products or whatever I have from within the question underneath each of the chemicals here. So I know from this particular reaction that I have 7.8 moles of magnesium. Now I've left a space here because I usually put masses at the top and then I convert them to moles, but because we were given in moles, I've already just started with the moles down below. So I have 7.8 moles of magnesium and I have 4.7 moles of oxygen. Of course, if I wasn't given the moles, if I was given mass of these particular compounds here, I could very easily convert them to moles. So here we go, I've got 4.7 and 7.8. Now, once you have the reactants in moles, what you're going to want to do is divide each of these numbers by their coefficients. So I'm going to take the 4.7 moles and I'm going to divide it by 1 mole, which is the coefficient in front of the oxygen. Even though we haven't written it, it is a 1. And then, of course, that will produce 4.7 as the number. Notice that there's no units on that. And then the next one is 7.8 moles divided by 2 moles, which is the coefficient in front of the magnesium here. And that will produce a value of 3.9. Now, why did I do that? I did that because if I look at my chemical equation here, for every 1 oxygen gas molecule, I consume 2 magnesium molecules, or in this case they're atoms, but 2 magnesiums. And as a result of that, the rate at which we consume the magnesium is faster than the rate that the oxygen gas is being consumed. As a result of that, we have to get everything into a 1-to-1 ratio here. So we want to divide by the coefficient so I can see how much comparatively number of moles we have between my reactants here. So you'll notice that the smaller number here is 3.9. So I have 4.7 and 3.9. The smaller number tells us that this is the limiting reactant. Now that looks a little bit confusing because, well, I have 7.8 moles, which is greater than 4.7 moles. Why is it that the magnesium is going to run out first? And if you recall, I just said to you that the magnesium is consumed at a faster rate. There are 2 magnesiums consumed for every 1 oxygen. And so I have to determine basically a number of atoms for number of atoms, or number of molecules for number of molecules, which one will be consumed the fastest. So in this particular case, my magnesium is going to run out first. It is our limiting reagent, which means that my oxygen here is my excess reagent, which means I'm going to have some oxygen left over. So let's go ahead and continue answering the question. So in this particular case, we've already gotten to moles of magnesium. Now, when we want to find out how much of a product is produced or how much excess is left over, we always use the limiting reagent's number of moles because we know it's going to be the one that's going to run out first. As a result, we can use that number of moles to actually calculate out. So it says here how much of the magnesium oxide is created. And so I've already converted magnesium into moles. I can connect the two, and you'll recall from last class that we can do a ratio. So we have a 2-to-2 ratio, which is the same thing as a 1-to-1. So I actually have 7.8 moles of my magnesium oxide that is being produced. The question doesn't ask for moles, it does ask us to convert it into grams, so let's go ahead and do that. I'm going to take that number of moles and I'm going to multiply it by the molar mass of the magnesium oxide. Here, of course, the molar mass of magnesium oxide is 40.3044 grams per mole. And so moles will cancel and I'll be just left with grams at 314.37 grams. So this is how many grams of magnesium oxide will be produced. Now, let's say you chose the wrong limiting reagent. Let's say you chose oxygen being the limiting reagent. When you do the calculation, the number you produce will be greater than 314.37 grams because if oxygen was the limiting reagent, all the oxygen would get consumed. And of course, we know in this particular case, oxygen has more moles, more in terms of the amount of oxygen than magnesium in this particular case. So the number we get should be greater than 314. I didn't do that calculation, but if you want to try it out, check it out. You'll notice that it is larger, and that's because there is more oxygen present than there is magnesium. The question also asks us to determine how much excess reagent is left over. So let's go ahead and do that. Well, my excess reagent we know is oxygen. So I'm going to take my limiting reagent's number of moles and I'm going to use that to determine how much excess reagent is left over. So when I do that, I can hook up a molar ratio. Remember, we're moving in this direction here. We moved in that direction last time. You, of course, divide by the first number you interact with and multiply by the second number. And so as a result of that, we end up with 3.9 moles of oxygen that will get consumed. So this number here is how much you have, and this number is how much will get consumed. And if I want to find out how much is left over, I just take the difference between the two. So I'll subtract them out. So 4.7 less 3.9 leaves us with 0.8 moles of the oxygen left over. So that 0.8 moles will stay in the reacting vessel while the reaction finishes, and it will just remain there with the rest of the magnesium oxide that is present. Okay, so that's how we solve this problem. Now this problem was a little bit more simple, so let's move to another problem that's a little bit more complex. It's got a couple more steps in there, and that's this one here. It says here, what is the greatest amount of aluminum chloride that can be produced by reacting 114 grams of aluminum with 186 grams of chlorine gas? And then it says how many grams of excess are left over. So there's a little bit of wordiness to it. But again, the steps are the exact same. The first thing we got to start off with is our balanced chemical equation. We know that we have aluminum reacting with some chlorine gas. So chlorine gas is diatomic, aluminum is a solid, and that will produce some aluminum chloride, AlCl3, and that's a solid. As a result of reading the question, we're able to determine that we have 114 grams of aluminum and 186 grams of chlorine to start with. Now, of course, before we start doing any of the calculations, we do need a balanced chemical equation, so I will balance this chemical equation as follows. Now, in order to do anything in chemistry, we do need to convert it to the mole. And so here we go. I will convert these into moles. I'll take my masses and I will divide them by the molar masses of the actual compounds that we're dealing with. So it's 26.98 grams per mole, which means grams will cancel. And that leaves me with 4.23 moles of aluminum. And then, of course, I'm going to divide by 70.9 grams per mole, 9 grams per mole of chlorine to produce the 2.62 moles of chlorine that are present there. So just like in the last question, I'm going to take these number of moles and I'm going to divide them by their coefficients. So I have 4.23 moles divided by 2, which is the number of moles of aluminum in the stoichiometry, the stoichiometric ratio there. And that produces a value of 2.11. And I will do the exact same thing with my chlorine. So I have the 2.62 moles, and I will divide that by 3, and that will produce, and I should say 3 moles, so these all cancel out, and so you end up with 0.87. So we know already that this is the limiting reagent and this is the excess reagent here. So I know this guy is limiting, this guy is in excess. I should say BR. There we go. That excess reagent and that limiting reagent are able to then determine, or we can use that information to help us determine what it is that the question is asking us. So this question says, what's the greatest amount of aluminum chloride that can be produced from this amount of chlorine? And so we have a ratio here of 3 to 2. And when I do that ratio, again, I'm moving in this direction, divide by 3, multiply by 2, I have 1.75 moles of aluminum chloride produced. If I want to determine the mass, I can just take that and I can multiply it by the molar mass of the aluminum chloride at 133.34 grams per mole. I know that when you guys are doing this, this may take you a little bit longer because you actually have to calculate the molar masses. I've already done that. When I do that, of course, moles cancels out. I'm going to be left with grams. So you'll notice the steps is always the same here. It's 232.9 grams. So that is the mass, the maximum amount of mass of aluminum chloride that I can produce given these amounts of aluminum and chlorine gas. This question also asks us to determine the amount of excess reagent left over, but it asks for it in this particular case in grams. So let's go ahead and do that. I'm going to take my limiting reagent. I'm going to determine how many moles of the excess reagent is consumed. So again, I'll look at the ratio. It's a 3 to 2 ratio between that. And that will produce 2.11 moles of aluminum, I guess I should say consume 2.11 moles of, pardon me, I wrote down the wrong number here. It's not 2.11. The number is 1.75 moles. So I have 4.23 and I consume 1.75. If I take the difference between the two, I'm going to be left with 2.48 moles of aluminum. And of course, if I take that 2.48 moles of excess, that's the stuff left over after the reaction happens, I can take that number and I can multiply it by the molar mass at 26.98 grams per mole. And that leaves me exactly with 67 grams. 67, actually, yeah, correct answer is 67.00 grams of excess reagent. And so you guys can see that the process is always the exact same when you're solving these problems. It's mass to moles, determine which one's limiting, use that limiting and its mole ratios with everything else in the problem, and you should be able to determine everything there. If you guys have any questions, send me an email and we'll go from there. Thanks, guys.